Hello everybody and welcome to part 2 of the FuzzBeard Industries Pedal Building Academy of Pedal Building, Electronics, Pedal Primer, whatever you want to call it. I'm still not sold on either of the names, but whatever. Welcome to part 2 where we are going to discuss capacitors. We're going to cover the basic information you need to know on the different types of capacitors, how to identify them in the wild, so to speak, and also in circuit diagrams with the various symbols that you might find for capacitors, and generally how you would use them within a circuit. We're also going to cover how to read the different values on the capacitors. Obviously, capacitors come in a number of varying different sizes. Some of them have different labeling to others. Some of them just have the value written straight on the body. Others have a little code that you've got to work out to find out the exact value. But anyway, having learned about resistors in the previous video, it's time to check out the next most common component found in guitar pedals and circuitry in general: capacitors. Capacitors and their function, capacitance, are measured in farads, named after famed scientist Michael Faraday, someone who you've probably all studied in school at some point. The farad itself is actually quite a large unit and certainly beyond what you'd find in any guitar pedals out there. So for guitar electronics use, the farad is subdivided into smaller ranges. Microfarads, or 1/1,000,000th of a farad. This uses the prefix Greek letter mu, but is often referred to with a small u and a capital F due to the lack of Greek characters on most Western keyboards. Next up is nanofarads. This is 1/1,000,000th of a farad and uses the prefix n, a small n, for NF. Picofarads, this is the smallest one you're really going to use in most pedal building, and this is 1/1,000,000th of a farad. This uses the prefix of a small p for PF, picofarads. Now these lads all come in various forms, most notably electrolytic. These occupy the entire microfarad range and are easily identifiable by their cylindrical bodies. They're often polarized, so current will only pass in one direction. The correct orientation is aided by a white stripe on the body of the capacitor pointing to the negative leg. Polarity is also indicated by a shorter leg on the negative side. Be sure to pay attention to this, as it has the potential to really mess up your day if you get them the wrong way round. Due to their comparatively large size, the capacitance is usually written in full on the side of the body, denoted by a number followed by the UF suffix. Non-polarized electrolytics also exist but are rarely used. I have seen them in some old wire pedals and tube screamers, but that's about it. I'm not sure why these were used in place of the more common polarized ones, but given the nature of pedal building in the old days, it was likely that that was what they had in the parts bin at the time. If you do know why, then please drop your knowledge in the comments, as I'd love to know. Next up is poly-plastic film. These usually come in a small rectangular case or dipped in epoxy lacquer, often known as a polybox. These tend to occupy the full nanofarad range and also sometimes reach into the microfarad range. The value is either written on the body as an expression of NF or nanofarads or microfarads, or sometimes a code is used to display the capacitance instead. This generally tends to depend on the manufacturer. Similar to the coloured band system that you see on resistors, capacitors use a 4-character code to display the capacitance in picofarads. The first 2 numbers being the value, the third number is the multiplier, so tens, thousands, etc. The 4th character is a letter that denotes the tolerance, commonly 1, 2, 5, 10 and 20%. There are other values, but these are the ones that you'll generally tend to encounter most. Next up is the ceramic disc capacitor. These are small, cheap, circular, usually like a reddish or orange kind of color. They occupy the picofarad range and the very lower end of the nanofarad range. Due to their smaller size, these tend to utilize the same code as the ones that you see on some polybox capacitors. Another type of capacitor to be aware of is surface mount capacitors. This is something of a bonus item for this list, as it's not really a type of capacitor, more of a class of component in itself, as you get all manner of surface mount components from resistors, capacitors, op amps, diodes, all that sort of stuff. But surface mount, or SMD, surface mounted devices, these components are typically much smaller than their through-hole counterparts, and often used where small board sizes are required, allowing a much more densely populated board that would be impossible to achieve with through-hole parts. As the name suggests, they are mounted directly onto the board rather than through a hole as with the quote-unquote normal parts, and then they are soldered in place. This guide is intended for through-hole components though, so aside from informing you of their existence, that is about as far as we'll be going with SMD stuff for the time being. Capacitors are identified as either axial or radial based on where their leads are connected to the body, with radial capacitors being the most common configuration. Radials have both legs coming out of the bottom of the body, meaning that they stand vertically on the board like a little top hat. This is opposed to axial capacitors, which have the legs coming out of each end, much like a resistor. Axial capacitors are mounted horizontally on the board, and obviously they take up more space, hence their reduced popularity, especially where PCB real estate is limited. You are more likely to find axial capacitors on vintage pedals and audio amp builds, where the enclosures were larger and there was a bit more space to work with. Now, both ceramic and film capacitors are non-polarized and configured with radial leads. Axial versions do exist, but they are comparatively rare. Radials are the type that you will nearly always encounter due to their space-saving properties when compared to the axial versions. The general consensus is that audio designers tend to go for film capacitors over ceramics if the option presents itself, as the film capacitors tend to have a better audio performance and are better suited to performance-critical applications. For example, you don't want a noisy preamp or a delay. Ceramics can be a little harsher than their film counterparts in the audio chain, so are generally used where they are the only option available, kind of in terms of size or value. Try breadboarding two of the same circuit using ceramics only in one and film caps only in the other, and see if you can notice the difference. Voltage rating. The other important bit of info that you'll find on the body of a capacitor is its voltage rating. This is important because it affects the size of the capacitor far more than its capacitance does. You can have two capacitors of the same value but different voltage ratings, and they'll be two very different sizes. Common voltage ratings are from 16 to 63 volts, certainly no more than 100 volts, as they will start to encroach on the territory of other components in your build with their imposing bulk, and you might have trouble fitting everything in, especially if you're building a board design with a tight layout. Most pedals use a 9-volt DC power input as standard, so for those pedals ideally you don't want to go below a 16-volt rating, as the next rating down is 9 volts, and the component may fail if you get a little too much power through your circuit for any reason. There are also some units out there that run on 12 volts or an 18-volt supply, so if you're building one of these, then make sure you select your capacitor voltage ratings accordingly, aiming for at least the next value up from whatever supply voltage you're using. Now, as far as how they work on an electrical level, i.e. how the electrons behave when passing through a capacitor, I'm not going to go into that as it's a little bit beyond the scope of what we need to know for our purposes right now. There are a ton of great resources out there if you do want to go and learn about that aspect though, but let's get onto their uses next. Applications. Capacitors have many uses in audio circuits, some of the most common being filtering, e.g. as part of a tone control, also used to set the frequency response of a circuit at the input and output. Capacitors act as a high-pass filter, cutting frequencies below a certain threshold determined by the capacitor value. Smaller value caps have a higher threshold, whereas larger values will allow more low frequencies to pass and thus have a greater low-end response. So for example, a guitar pedal would have a relatively small input cap value to ensure that only the useful guitar frequencies would be allowed to pass through to the effect, whilst filtering out the unwanted lower frequencies that would otherwise make the sound too muddy. As a bass guitar resides in a much lower frequency range, a bass effect pedal would require a larger input capacitor value to allow more of these lower frequencies to pass and ensure that you're not cutting out any of that valuable low-end goodness from your bass sound. For example, I have built pedals in the past that have had different input capacitor values on a switch marked light and dark to allow different low-end responses. You could potentially do the same with values suited to guitar and bass and switch up according to which instrument you're playing through the effect. Just make sure the output capacitor is large enough to pass the extra low end from the bass as well. You could even do this with two capacitor values and a potentiometer to simulate a variable capacitor and create your own controllable high-pass filter. Just changing the in and out capacitor values on a guitar pedal does not necessarily make it suitable for a bass. Depending on the circuit, there may be other part values that need tweaking. For example, the differential gain circuit in a Proco Rat pedal separately controls the frequency responses and distortion levels of the frequencies either side of 1.5 kHz. You might need to alter some of those part values to better suit your bass sound. Another use is coupling and DC blocking, so this is used to connect the different stages of a circuit. As you spend more time learning to understand schematics, you'll notice there is a capacitor between each stage of a circuit. These are used to allow AC signal to pass from one stage through to the next whilst blocking any DC signal. DC or direct current signal is used to power the circuit, whereas the audio signal from your instrument is in the form of an alternating current. Now, whilst you do want the AC or audio signal to pass from one stage to the next, you do not want the DC or power signal to do the same, or it will introduce unwanted noise into your audio chain. Each stage that needs DC voltage to power a component, such as a transistor or an IC, will have that voltage supplied via an individual connection routed from the power supply to the required stage. This means that each stage is able to receive the voltage that it needs from the power supply, but that the DC signal from the power supply does not pass between the stages and interfere with the audio. A third use of capacitors in audio circuits is a technique that is known as smoothing. Smoothing capacitors are used to level out any remaining imperfections in power supply signals from cheap power adapters or improve the sound of the audio signal post-clipping. Power adapters, aka wall warts, receive their power from the main socket in the form of a 220 to 240 AC voltage, or 110 volts, aka freedom voltage if you're in the US, and using a transformer converts it down to a more manageable 9 volts. A 4-way diode bridge rectifier is then used to convert the signal from AC to DC, the idea being that you'd flatten out the oscillations of the AC waveform and have a nice stable DC supply. However, in practice this is rarely the case, and there is often still some ripple left in the waveform after the rectifier, meaning noise will still be introduced into your audio signal from the power supply. A large value electrolytic capacitor, 100 microfarads or so, can be inserted between the power input and ground to further improve the noise reduction in the converted power signal. If there is still high frequency noise present, then a small value capacitor in the mid-nanofarad range placed between the power and ground rails will also help eliminate that. Small value capacitors, for example 100 picofarads to 1 nanofarad, can also be used in parallel with a clipping diode setup to smooth out the clipping sound. These are also found on the transistors in fuzz face-based designs as well. Sometimes the clipping effect of the diodes or transistors can be a little harsh in the high end, and using a smoothing cap in this application helps clean up the high end and make it a bit more pleasing to the ear. You could even add them on a switch to allow optional smoothing. More on switches later. Capacitors do have other functions as well, but these are the most common uses in guitar effects and especially fuzz pedals. You will notice that pedals with battery-only power don't tend to have a power filtering section, as a correctly functioning battery produces a near-perfect DC power supply which does not need filtering. If you do decide to mod one of these battery-only units with a DC jack to allow you to power it from a wall adapter, a common modification that you'll see on a lot of old Russian big muffs for example, you will likely encounter some or a lot of noise depending on the power supply you're using with the pedal. While some adapters have power smoothing components built into them, many do not. So to preempt the potential noise issues caused by a poor quality adapter, it is best to install a power filtering section along with the DC jack, so you won't have to suffer the indignity of a noisy pedal when you inevitably forget to bring your nice expensive power supply to a gig one time and have to borrow a crap one for the night. Okay, and finally we are going to cover how to identify capacitors within a schematic diagram. As with resistors, there is more than one type of schematic symbol that you will see for capacitors as you read more and more circuit diagrams. Generally the most common one is two black rectangles with a lead, with a line leading off of each one. The leads represent the legs of the capacitor and the two thick rectangles represent the charging plates within the capacitor. If both of those rectangles are black, that indicates it is a non-polarized capacitor and will pass signal in either direction, so it does not matter which way round you put it in your circuit diagram or which way round you install it on the circuit board itself. Polarized capacitors, which only allow signal to pass in one direction, they will be denoted with a black and a white rectangle, or if not, there will be a little plus symbol on the positive plate, so that will tell you the correct orientation for that polarized capacitor. There are also American versions of the capacitor symbol, which is a straight line and a curved line to indicate that it is a polarized capacitor as well, but generally I tend to use the non-US version. Please do the old like and subscribe dance, you know the score by now, and tell your friends, and look forward to checking out the next video. See you later.